Good afternoon. All right, so we are continuing with chapter 6. So your exam is going to be after this chapter. We need 2 classes to finish this chapter. So today and Tuesday classes we will use for finishing the chapter. So the exam is on Thursday, next Thursday. Okay? What is the date? Four, 5, and 6. All right, so the next topic, so last class 2 weeks ago when we stopped, we had discussed limiting reactants. Now the next topic we are going to discuss is percent yield. So when we perform an experiment in the lab, when you perform a reaction, and if you weigh or if you measure the amount of product you have obtained and compare that to what you were supposed to get or what you could calculate from the limiting reactant principle, you will always find that what you actually obtained in the lab is always less than what you were supposed to get. Okay, so what you obtain in the lab is usually called actual yield, and the theoretical yield is what you are predicting using your calculations. Like you will look at the balanced equation and you can figure out who is the limiting reactant, and we know that the limiting reactant determines how much product that can produce. So when you calculate that, you will say, okay, I'm supposed to get this many grams, but I'm only having an amount which is lesser than that. So the actual yield is what you got and theoretical yield is what you calculated. The ratio of that is known as percent yield. So yield again could be calculated using the amount of product in mass units, that is in grams or moles or even number of molecules. So percent yield can be calculated using this very easy equation. As I said, it's the ratio or actual yield over theoretical yield. So A over T multiplied by 100%, because we express this as a percentage. So we will multiply that by 100. So again, percent yield describes how much of a product is actually obtained relative to the amount that should form from the stoichiometry calculations. Why we will not get what you were supposed to get? Why in reality your amount is always less? When we calculate or when we use the limiting reactant and assuming that all the limiting reactant is reacted, so a particular amount of product is formed, we are thinking in a ideal situation, like every single molecule of the limiting reactant is going to react and it is going to form product and everything is perfect, like the temperature, pressure, all the other variables which can affect a chemical reaction. We are assuming everything is perfect. But when you actually do a reaction or when you perform something in the lab, all conditions may not be perfect and all single molecules of limiting reactants may not be reacting. Okay, and because of all those factors, we will always get a few grams or a lesser amount than you would calculate. There are some reactions you can go very close to the theoretical yield. There are some reactions no matter what you do, you will always have a considerable amount less than what you would predict. So let us look at a chemical reaction here. Sodium chloride formation, the balanced equation is given there. If we have 0.2 moles of chlorine and it is reacting with excess sodium, meaning thereby you don't even have to worry about, who is the limiting reactant in here. It is clear from that sentence, right? If sodium is in excess, who is the limiting reactant? Chlorine. So you have 0.2 moles of chlorine and 0.4 moles of NaCl are produced. What is the percent yield? So when you look at the balanced equation, what is the mole ratio, or what does it tell you? 1 mole of chlorine will produce 2 moles of sodium chloride. So if you have 0.20 moles of chlorine, how many moles of sodium chloride you should get? 0.4. And in this case, you have got 0.4 moles. What does that mean? If you calculate the percent yield, what would you get? You would get 100%. So both, as I just said, theoretical moles or theoretical yield is using the limiting reactant, and mole ratio, you predicted how much you should form, and that is what actually is formed. So in this case, the percent yield is 100%. Again, this is just a question, put on the PowerPoints for you to understand the concept. In reality, there are, I can say probably there are no reactions that would give you 100% yield. So percent yield is 100%. Here is the same question, but now we have different amounts. This is more closer to the reality. Okay? So here again we have sodium is in the excess reagent, and we have 0.450 moles of chlorine, and we produced 0.385 moles of sodium chloride. What is the percent yield for the reaction? How do we calculate this one? First we need to calculate how much sodium chloride should be produced according to the mole ratio, correct? So if we have, let me get the pen. So the limiting reactant, we have 0.450 moles of chlorine. So how much sodium chloride should be produced? How do I calculate that? What mole ratio I should use? 2 moles of NaCl per 1 mole of Cl2. Yes. So I will get the number of moles of NaCl that should be produced. How much is that? 0.450 multiplied by 2 will be 0.900 moles of NaCl. So this is your theoretical yield. This is what you call the theoretical yield. Okay? What you would calculate using the amount of the limiting reactant and the mole ratio from the balanced equation. Now let us see, how much did you actually produce? 0.385 moles. Therefore, percent yield. What is percent yield equation? Percent yield is A over T multiplied by 100. Remember that. It's one of the easiest equations you can get from this chapter. Okay? A over T, A for actual, T for theoretical. So when you just plug in the numbers, 0.385 is your actual yield, and theoretical yield we just calculated 0.900, multiply that by 100%. What is our percent yield here? $42.8. Everybody is good so far? Yeah, we have everything just on top of what I wrote. Let's look at another activity. A student was synthesizing aspirin in the lab. Using the amount of limiting reactant, she calculated that the amount of aspirin that should form as 8.95 grams. When she weighed her aspirin product, what she produced in the lab, on the balance, its mass was 7.44 grams. So, which is the actual yield of aspirin from this problem? 7.44 grams. Which is the theoretical yield? 8.95. And what would be the percent yield? So, percent yield would be we will put 7.44 in the numerator and 8.95 in the denominator and then multiply by 100. What is it, David? 83.1%. That is good. She did good. Something that gives you, 80 or above is considered good. So there is your answer slide with this problem. All right, let's have a clicker question on percent yield. And here is the easiest question of this chapter. Ammonia is prepared from the reaction between nitrogen and hydrogen according to the equation. What is the percent yield for this reaction if the theoretical yield was 17 grams but only 15 grams are collected? You all have clickers? Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. $30 seconds more. How much time we need for this one? 10 seconds? That is if you have a calculator. Did I count 17 or 16? Oh, okay. How should I set up this one? 15 divided by 17 multiplied by 100. What would we get? 88%. Yes. Okay. So we are on to the last part of this chapter. We are going to discuss energy changes that are associated with chemical reactions. So when you react methane with oxygen, when you burn methane gas with oxygen, like what you use in a Bunsen burner, it is obvious that there is a lot of heat produced and you use that heat to boil the stuff, right? If you are using that, the propane that you use in your grill, or natural gas, if you have natural gas lines to your home for your stove, the heat produced is used for boiling water and cooking food. A lot of chemical reactions, basically all chemical reactions and physical state of physical state changes are associated with some sort of energy changes, and a lot of chemical reactions actually release energy when the bonds are broken and the new bonds are formed. And we haven't discussed in details about the bonds. We will look into chemical bonds, I think in chapter 7 or 8, which is coming after this exam. But energy changes that occur in a chemical reaction actually comes from the breakage of bonds and formation of bonds. Okay? And most of the chemical reactions would release some sort of energy, and some chemical reactions would absorb some sort of energy. So all chemical reactions are accompanied by some energy change. Now before that, let us just look at the law of conservation of energy. Remember that we introduced energy in chapter 1. We said energy is the ability to do work or transfer heat, and there are two main forms of energy, kinetic energy and potential energy. Kinetic energy is the energy of motion. Potential energy is energy that is stored in a compound or in an object by its position. And all other forms of energy that we talk about, light energy, heat energy, mechanical energy, electrical energy, chemical energy, everything is either kinetic energy or potential energy, which is being, what is that? I think the speakers are on. Hope that will take care of it. So energy we can convert from one type to another, and as I was just saying, all the forms of energy we usually see in our day-to-day life, it's all can be categorized as either kinetic energy or potential energy. Now, law of conservation of energy says that actually energy cannot be created nor destroyed. We can only convert a form of energy to another form and another form and another form. So energy keep getting transferring from forms to forms. The total energy of the universe is a constant. That is the first law of thermodynamics, which comes from the law of conservation of energy. So when energy is released from an object, something else is actually absorbing that energy. So when a chemical reaction is producing energy as heat, that heat is released to the atmosphere. Well, we will say, oh, heat is produced and it is lost. Actually, it is not lost on a thermodynamic point of view. The atmosphere is actually absorbing it or receiving it. Right? So that is the law of conservation of energy. So energy, we cannot create or destroy energy, and whatever energy is transferred in a chemical reaction, it can, when a chemical reaction releases energy, something else would absorb that same amount of energy. So the amount of energy released is equal to the amount of energy absorbed by the surroundings. What picture you are seeing here is your car, internal combustion engine, which uses octane, burns that with oxygen, and a lot of energy is released in the form of heat. Some of it is used to make your car run, which is actually useful form of energy, and most of it is lost as heat. If you look at the overall efficiency of an internal combustion engine, only 32% of the energy is converted to work, or only to 32% of energy produced from the combustion of octane and oxygen is used in the form that you want, that is to run your car. Rest is actually lost to the surroundings or lost to the atmosphere as just heat. Because when octane burns with oxygen, when the bonds break, they release lots and lots of energy. So we will also look at what do we mean by efficiency. That is something which we hear all the time. How can we improve efficiency, right? Or energy efficiency. We talk about that all the time. Efficiency is actually the amount of energy that would end up as useful work. It is a measure of the amount of energy that would end up as the work you need to see from a particular instrument or a particular conversion or a particular reaction. Now, no conversion is totally efficient. Every single conversion will lose a little bit of energy to the surroundings in the form of heat. And again, efficiency is the percentage that ends up in the useful form. Now, just for an example, if you consider one of those light bulbs, not those energy efficient light bulbs, the old fashioned light bulbs, and what is the efficiency? And if you start with the chemical energy released from coal, and this is the useful form you want to have the light in your room. If you start from the beginning and walk through the conversions, we will see actually the overall efficiency is only 1.6%. The energy released by coal, 1.6% will end up as light energy which you want to see. Rest is lost along the pathway of all these various conversions. Here is a breakdown. The coal which you use in your steam boiler, 88% of the heat energy is used to heat your water to steam, and 46% of the heat energy from the steam is used to run your the steam turbines. This is a good efficient conversion. 98% of that energy gets converted to electrical energy. But when you use that electrical energy in the form of light, only 4% ends up as light. Where is the rest of it? Just in this conversion itself, where is the rest of it? Released as heat. If you ever have touched one of those light bulbs which has been burning for some time, you can actually cook food on that. It's that hot. So much energy is being wasted as heat. That is where the newer energy efficient ones comes in. And if you ever have touched, I'm not recommending anyone to go and touch light bulbs, okay? You might burn yourself. But if you have, comparatively, even if just you feel with the hand, those ones are much, much cooler even when they operate for a long time. And that is where the efficiency comes from. Most of the efficiency comes from. Okay? It's not producing as much heat, or it's not wasting energy as just converting electrical energy to heat energy and just losing it to the atmosphere. So that is, the step-by-step efficiency, as you can see, but the overall efficiency when you compare with coal to the light, it's only 1.6%. So we already said all chemical reactions, either they release energy in the form of heat or they absorb energy in the form of heat. The reactions that release energy to the surroundings are called exothermic reactions. Of course, thermic means everybody knows we're talking about heat. Exo, think about exit, out. Exo means out. Heat out. Exothermic means reactions that produce heat and release them or heat out. The opposite process, or some reactions, as you know, they won't happen even at the room temperature. Some reactions you may have to heat it a little bit, you may have to warm it a little bit. So those reactions are endothermic reactions. In order for those reactions to happen, it should absorb some amount of energy from surroundings. And cooling them, what is getting cooled if you absorb energy from surroundings? The surroundings gets cooled. From wherever you take heat away, that gets cooled, right? So endothermic reactions and exothermic reactions. Here is an example of exothermic reaction. Hydrogen and oxygen combining together forming water. You have seen this before also. It is a highly exothermic reaction, formation of water from its elements. And endothermic reactions I don't know what they are showing in the test tube. Have no idea. Probably you might have a better idea from the book if you look in that picture and the footnote. But it's typically showing a test tube that is being heated, therefore a reaction is happening because that reaction needs some heat input. You don't have that picture in the book? Huh. Maybe they forgot to take it out. It might be then from a previous edition. Says page number 236. It's not there? Okay. Wait a second. Figure 5.5, 5.8. Is it from chapter 5 pictures? Maybe that's why. These pictures are just taken from chapter 5 and put it in there. That's why. Anyway. So we just said exothermic reactions and endothermic reactions. So why do some reactions would release heat and why do some reactions would require heat? If you look in an energy profile or the potential energy of that particular substance, in an exothermic reaction, the reactants, those molecules in their bonds, they hold so much energy, and when they form products that hold lesser energy in their bonds, the difference in that energy is released as heat to the atmosphere. Again, opposite for the endothermic reactions, the reactants hold less amount of energy in their bonds and they are forming products that are holding higher amount of energy in their bonds. So that difference of energy should be absorbed from the atmosphere. So that is exothermic reactions and endothermic reactions. And in each case, what happens to the temperature of the surroundings? In an exothermic reaction, what happens to the surroundings? The surroundings get hot or surroundings get cooled? The surroundings should get hotter because it is releasing heat to the surroundings. And in an endothermic reaction, the surroundings should be getting cold because it is absorbing heat from the surroundings. Okay, now we are going to do quantities of heat. So how do we measure this heat energy? First word of caution, please do not assume heat and temperature are one and the same. It is not. Even though we kind of use, in day-to-day life, kind of both in a same way or same manner, heat and temperature are two different things. When we say temperature, it's just a measure of how hot or how cold something is relative to a standard. Whereas heat, when you use that word in chemistry or in physics, heat means it is the amount of energy. Okay? And it is not just depend upon how hot or how cold something is, it depends upon other things also, which we will look at right now. Before that, let us first look at what are the units of heat that we would use in chemistry. So the heat energy that is transferred between two objects, because there is a difference in temperature. They are related but not one and the same. Now the quantities of energy or heat are usually expressed with units called joules. Joules, and capital letter J is the denotation for joules, or calories. Calories is also used. This is the older unit. Mostly joules is what you will see in the newer books or in newer calculations. Here is the conversion between calorie and joule. Calorie is based on properties of water, whereas joule is more common to any substance. So 1 calorie is exactly 4.184 joules. Now when we say calorie, do not think that that's the same calorie as you see in the labels of your food items. That is the nutritionist calorie, which we usually write with a capital letter C. Here note that we use a small case letter C for calorie, and short form also we use small case letter C, CAL, cal. Here we will use a capital letter C, and that is actually a kilocalorie. So 1 nutritionist calorie is 1000 small calories or 1 kilocalories, because kilo means 1000. So here it looks like it's a cereal box, or I don't know, 1 cup it says, and calories 190. So probably it's a cereal box. Let's assume that. Okay. So when it says it gives you 190 calories from 1 cup, it is actually 190 nutritionist calories you are talking about. Okay, not the small case letter C calories. Now, in order to calculate heat, as I said, heat depends upon a couple of things, not only just the temperature difference. So we are going to look at a quantity called specific heat. Okay. Now, specific heat is defined as the heat required to increase the temperature of 1 gram of a substance by 1 degree Celsius, and it depends upon the identity of the substance. Okay, because for each substance, specific heat is a constant. Like for water has a specific heat, versus copper metal has a different specific heat. And again, it is the amount of heat energy required to raise the temperature by 1 degree Celsius of 1 gram of a substance. Now, specific heat units are joules per gram degree Celsius, because that comes from the definition. Joules is the amount of energy per 1 gram of a substance, temperature to be raised to 1 degree of Celsius. So specific heat of water is actually 4.184 joules per gram degree Celsius. You don't have to memorize any specific heats, which this would be given to you when you use in a calculation. Here is a table that shows specific heats of some of the substances, even some of our day-to-day substances also. Here are some of the metals and non-metals, pure metals and non-metals, and their specific heat given in both units, that is joules per gram degree Celsius or calories per gram degree Celsius. And then we have substances, water, solid, meaning thereby ice, liquid water and gaseous water. The 4.184 we saw is for liquid water. And then we have things from our daily life. Strawberries, olive oil, cheese. So it's again just for a comparison or idea. Well, what can we kind of look at this table and see? Look at the metals and their specific heats. Say for example, aluminum, copper, gold, lead, silver, tin. Look at the specific heats of metals compared to, let's say, water. A lot less, right? When you think about in real life, if you want to heat, let's say 1 gram of water versus 1 gram of a metal, okay? Which one will take more time if you are using the same source? Metal might take less amount of heat. That's what the specific heat says. Okay? Specific heat is the amount of energy required to raise the temperature by 1 degree Celsius of 1 gram of a substance. So if specific heat is low, that means you need less amount of energy to raise the temperature. If specific heat is high, then that means you need high amount of energy to raise the temperature. Okay? And that is why metals get hotter fast. When you compare metal to, let's say, brick, or brick also will get hot fast. What else? Something like I guess water is the best example if you compare metal and water. Metal will get hotter very fast. Now, we are going to calculate or quantify the Q or the heat. Heat is usually represented in thermochemistry using the letter Q. And heat is dependent upon three things: mass of the object, specific heat of the object, and the temperature change. Three things, okay? So this we can put it into an equation. Q is equal to mc delta T. Please memorize this equation. This is an important equation. You will have a calculation based on this equation in your exam. We are going to do calculation using this equation right now after this discussion. So as I said, Q stands for heat, M for mass of the object, C for specific heat, and delta T. Delta means, delta represents a change always. So delta T means change in temperature. Now how do you take change in temperature? It is, the sign is important, whether it is positive or negative. So remember, delta T is T final minus T initial. Whatever is the final temperature minus whatever is the initial temperature. So depend upon that, whether a substance was getting hot or cool, delta T could be positive or negative, and that would affect the sign of Q. Therefore, when you look at the sign of Q, you will be able to predict a reaction is endothermic or exothermic. That is why the sign is important. Okay? But remember that equation, Q is equal to mc delta T. So we are going to practice this equation in couple of ways. So let us do this simple questions given right below the equation first. How much heat must be added to 15 grams of water to increase its temperature from 25 degrees Celsius to 75 degrees Celsius? Something that is not given in your problem, which I will give you always, is specific heat of water is 4.184 joules per gram degrees Celsius. So we can directly apply the equation here. We have everything given here, right? Okay, first of all, what is delta T? Read the question. Delta T is T final minus T initial. What is the final temperature here? 75 minus 25. So it is 50, which is a positive 50. Okay, now we can substitute everything into our equation. So Q is mass of water, 15 grams, multiply that by specific heat, 4.184, multiply that by delta T, 50. I haven't used the units here, but we can see grams and then joules per gram degrees Celsius. This is in degrees Celsius. So degrees Celsius, grams will get cancelled by those two. You will end up with J as the unit for Q. So how many joules of energy is added to this water in order to raise the temperature from 25 to 75? How much? 3,138 joules. How about the second question? What is the heat change when the same amount of water, 15 grams of water, cools from 75 to 25 degrees Celsius? It would be the same number but negative. Where do we get the negative sign from? From the delta T. In here, when you do the delta T, remember delta T is always Tf minus Ti. Here the final temperature is negative. The final temperature is 25 and the initial temperature is 75. So when you calculate delta T, you get negative 50. And then when you substitute everything into the equation, into the same equation, the Q equation, you are getting 15 multiplied by 4.184 multiplied by negative 50. Therefore, the answer is negative 3138 joules. So if I have to describe these processes as Endothermic or exothermic? Which one would be the exothermic process? Think in terms of, okay. Well, maybe let us hold that question right there. Let's just discuss a little more, okay? I have a slide which is specifically showing sign of Q and exothermic, endothermic. But you should be able to answer, you know, in here. Something is cooling down means what? It is releasing heat, right? So, the exothermic process should be the one that is in the bottom. Endothermic process is something that is absorbing heat. You read the question in the first one. Heat is added means what? The water is absorbing heat. So that is endothermic. But we will hold on to that discussion in a couple of more slides. And not couple of more slides, right here. Meaning of the sign of Q. So, now first of all, the words system and surroundings. Those two words, we would use that very often when we discuss thermochemistry. System is anything that you are interested in, the object you are studying, the chemical reaction you are looking at. That is called the system. Everything else is surroundings. Okay? So in our previous example, the water would be the system and everything else is surroundings. So if you look at the Q, and if Q is less than 0 means what is the sign of Q? Something less than 0. Negative. So if Q is negative, that means heat is released from the system to the surroundings. Heat is released means exo, heat out, exothermic. Okay? So let me write that down right here. Oh, where is my pen? I can't even see the pen in there. So if Q is negative, that means exothermic reaction. That amount of heat is released to the atmosphere. And the opposite, that is if Q is greater than 0 or if Q is positive, then it is an endothermic. It is an endothermic reaction. Okay? So now onwards we will focus on the sign of Q and we will say which one is exothermic, which one is endothermic. So here is another question. The specific heat of aluminum is 0.895 joules per gram degree Celsius. If 56 grams of aluminum at 75 degrees Celsius is cooled to 25.5 degrees Celsius, how much heat is transferred? What is the sign of Q and what is its significance? What is its significance means whether it is an exothermic reaction or endothermic reaction. Okay, how do we calculate Q? Q is mass 156 grams. Multiply that by specific heat, which is 0.895 joules per gram degree Celsius. Multiply that by delta T. What is delta T here? So initial temperature is 75, final temperature is 25.5. So 25.5 minus 75, which would give you negative 49.5. So negative 49.5 degrees Celsius is the delta T. So degrees Celsius, grams, grams, and you should have the answer in joules. How many joules? What is Q? It's straight multiplication, guys. Negative 1000. Negative 6911 joules. Well, let's look at the significant figures. How many we need? Well, we need 3 sig figs only. So we want negative 6.91 into 10 to the power. Okay. What is the sign? Of course, everybody can see. The sign is negative. What is its significance? Negative Q means what? It is an exothermic reaction, or this much amount of heat is released to the atmosphere when aluminum is cooling. Right there is your answer slide. Now, something called calorimetry. This is a lab which you will do next week. I mean, the Tuesday guys will do the coming week, and the Thursday guys also, yes. The next lab is calorimetry. Let's not put the date in there so that we are all on track. So calorimetry is the study of quantities of heat transferred between objects or in chemical reactions. So we use calorimetry to determine the heat of a system by measuring the heat change of its surroundings. Because it comes from the law of conservation of energy, the energy released by the system, exactly the same amount of energy is absorbed by the surroundings. Or the energy absorbed by the system, exactly that amount comes from the surroundings. So if you can measure either the heat change of the surroundings or the system, you know already the other one. It's numerically the same but opposite in sign. Okay? So in calorimetry, we will be able to measure the heat change of the surroundings, and from there we will be able to say what is the heat change of the system. Now, this is a coffee cup calorimeter which you would do in the lab. So in the coffee cup calorimeter, what you would do is you use the insulated coffee cups, put water in it, and then here we are talking about this metal sample which is called our system. So water will be your surroundings, and these are styrofoam cups just for the insulation, so that there is no heat exchange between the air and whatever you have inside your cup, or there is no heat exchange between your surroundings and the air. Okay? And what you would do is you will measure the mass of water you are putting it in. So you have the mass of water. Specific heat of water is a constant, 4.184 joules per gram degree Celsius. And we will use a thermometer to measure the initial temperature of water, that is before we put the sample in, and final temperature of water. So you have delta T of water. So you have all three things to calculate Q of water, which is your surroundings. Mass of water, delta T of water, and specific heat of water. If you can calculate Q of water, what is the Q of the sample? If you know the Q of the surroundings, surroundings is water, right? So if you know the surroundings Q, Q of the sample would be Q but negative, or I mean if you calculate Q for water, if it is negative, then the other one would be positive. So we would say the same numerical value but opposite in sign. Okay, so that is the principle of calorimetry, which you will do in the lab, and it is a pretty good experiment. We use coffee cups and thermometer and a hot piece of, you will heat a piece of metal and put it into measured amount of water, and you will calculate this. It is a pretty good experiment. So we are going to practice the calculation on calorimetry. Didn't you change your clocks?
Sorry, I had obligations.
What?
I had obligations.
Okay, all right. I just thought since you know it's 1:30,
Yeah,
You forgot to change your clocks. Anyway, so here is the question. A 92-gram piece of copper is heated and placed into a calorimeter with 100 gram of water at 25 degrees Celsius. So not that we know the mass of water, we know the initial temperature of water from this sentence. The final temperature of the mixture is 29.5. What is the mixture we are talking about? The water and the pipe. That is what the mixture here is 29.45. What is the heat change or Q of the pipe? First of all, if anyone is thinking, oh, Q is just put everything and straight away I get the Q of the pipe. Do I have all the information to calculate Q of the pipe directly? What is missing? The specific heat of pipe is missing, which of course I can look it up. Let's say it is copper, pure copper, so I might look it up. But something else is missing which you have no way of finding out. The initial temperature of the pipe. It just says the pipe is heated and put it into water. We don't know what was the temperature of the pipe before you place it into water. Right? Therefore, even if I provide you a table of specific heats for everything, you still won't be able to calculate the specific heat of the metal directly. So what we can do? We can calculate the Q of water because we have all the information for water. We have the mass of water, we have the initial and final temperature of water, and specific heat of water is a constant which I will be giving to you, 4.184. So we can calculate Q of water and then just change the sign, you have Q of the metal pipe. Okay? So that is the principle we would work on, and let us look at the calculation right here. So Q is equal to MC delta T, not that Q of water. Again, when you do the calculation, pay attention, use all the properties of water. There are two mass information given in the problem. Just to confuse you, the mass of the copper pipe is given there. Don't get carried away by using that along with other properties of water. Okay? Make sure that you will use all the properties of water carefully from the question. So mass of water, multiply that by the specific heat of water, multiply that by the delta T. So this is the final temperature, this is the initial temperature. So the difference is delta T. So you calculate that as 1860 joules. And then the rest is just the logic. So Q of the pipe is negative Q of water. So Q of the pipe is negative 1860 joules. And what does that mean? That is the amount of energy that is released by the copper pipe when it is cooling down. I have another question. This one we will do. We won't just look at the PowerPoint. We will do this calculation. A sample of metal alloy is heated and then placed in 125 gram of water held in a calorimeter at 22.5 degrees Celsius. The final temperature of water is 29 degrees Celsius. Assume that the heat exchange only occurs between the water and the alloy. First question, just a logical one. Was the initial temperature of the metal alloy greater than or less than the initial temperature of water? It must be greater than the initial temperature of water, right? Otherwise, how will the water temperature will rise from 22.5 to 29? Correct? If the metal was cooler than that, then actually the water should cool down. So that question is answered. And the second question is, what is the heat change of the alloy? So the same logic, since we don't have all the information for the metal, we will calculate Q of water and then change the sign. We have all information for Q of water. So Q of water would be, how do I calculate? Give me the numbers. 125 is the mass of water. Multiply that by, Yes, well, let us just do it in that order. Q is equal to mc delta T. Specific heat of water is 4.184. Multiply that by the delta T, which is 6.5. Final temperature is 29, initial temperature is 22.5, so the difference is 6.5. So this will tell you Q of water. So when we do these calculations, probably it's a good idea to, put a small notation W and M for Q of water and Q of metal so that you won't be confused which Q are you calculating. Okay? So Q of water, meaning thereby I have to use all the information for water. And what do I get for Q of water? 3,399. Well, let's use only 3 sig figs. Yes. So we want 3.40 into 10 to the power. This is Q of water, correct? So my question is, what is the heat change of the alloy? So what would be the Q of metal? Negative 3.40 into 10 to the power 3 joules. Exothermic or endothermic? Exothermic. The negative sign indicate that it is exothermic. 4. No, 4.184. Yep. Were you doing 4.814? Okay, yeah, 4.184. So yes, right there, that's our calculation. Why are they using only 2 digits? Is there anything given in the question with 2 digits? Oh, you know why? No, look at the delta T. But technically, the delta T is something which you derive, and I don't agree with that, guys. The delta T technically should be expressed with 3 sig fig as 6.50, and therefore your answer should be expressed through 3 sig figs. But, these power... No, I don't. I'm not taking points off. I'm just focusing on that because if any of you are going to do further like you want to go to engineering, when you go to higher level classes, there you will start focusing on the importance of sig figs. And at the 300 level, 400 level classes, you will be taken off points if you are not using the correct sig figs. So I'm just putting kind of a habit for you guys to look at the sig figs and pay attention to that. I'm not taking off points. Okay, let's have a clicker question. Calculate the Q to heat 873 gram of water from 5.4 degrees Celsius to 98.6 degrees Celsius. So I just want Q of water. That's all I'm asking you to do, and I have given you all the information. And you have the equation. You've been practicing that. So substitute all the numbers into the equation and calculate Q of water. Did you bring your clicker, Cameron?
Yes.
Okay. So I should have 18. All 18 from here. What is the setup? Q is 873 multiplied by 4.184 multiplied by how much? 93.2 will give you what? A big number. Well, I have already converted all that into scientific notation for you guys. 3.40 times 10 to the power 5 joules. Good. Okay, now, so we were just talking so far about heat changes, between an object and water, specifically, metal pieces. Now, how about heat changes in chemical reactions? If you want to measure how much heat was released by a chemical reaction using a calorimeter, what would you do? It works on the same principle. The heat change of the chemical reaction also is determined by the same way. That is, whatever is the heat released by the chemical reaction, it is absorbed by the surroundings. So again, you measure the heat change of the surroundings and change the sign. So that will tell you the reaction is exothermic or endothermic and how much heat is released or absorbed. Now, if the reaction does not take place in solution, such as a combustion reaction, think about it. You want to know what is the energy released when a specific amount of a fuel is burned. If you put that into water and try to burn the fuel, may not be a good idea, right? The reaction may not happen. So when you have some reactions like that, which you don't want to do it in solution, we will use something called the bomb calorimeter. Again, don't worry about the name. It's just that it's the same setup, okay, the calorimeter, but this time we have, kind of a really nice insulated cup, and we have a small metal cup inside that cup. And this metal cup is just separating whatever you are burning from the water. And since this is just a metal cup and it is placed in water, the combustion will happen inside the metal container and the heat is nicely transferred. The metals would transfer the heat very well, right? So that heat is nicely transferred to the water, and you are again measuring the temperature change in water and calculating Q of water and change the sign. You will get the Q of whatever substance or whatever chemical reaction you are looking at. So this small thing, since this is burning inside, we just call it a bomb calorimeter. It's not going to explode or anything, okay? So it's the same setup. As I just mentioned, when an exothermic reaction takes place, the water absorbs heat from the reaction and increases the temperature. So Q of the reaction would be negative Q of the calorimeter, or opposite Q of the calorimeter. Now, how about if we are given an equation and heat change for the reaction like this one? Hydrogen and iodine combine together forming HI, hydrogen iodide. The balanced equation is given to you, and it says the heat change Q for the reaction is positive 53 kilojoules per mole of iodine that reacts. First question, a logical one, is this reaction endothermic or exothermic? It is an endothermic reaction. How can you say that? Looking at the sign of Q. If Q is positive, endothermic, Q is negative, exothermic. Now the second question is, what is the energy change when 2.5 moles of I2 reacts? How do I calculate that? Or what is this 53 kilojoules? Read that again. 53 kilojoules per mole of iodine, meaning thereby when 1 mole of iodine reacts, it requires 53 kilojoules. So if you have 2.50 moles, how much energy is required? That's all it is asking. What would you do? Multiply 53 by 2.5 and that will tell you what is the energy you will need for 2.50 moles, and that is positive 133 kilojoules. Guys, I think I finished the chapter, didn't I? We are moving the exam. Well, we lost a class. I absolutely don't have extra time. That's the problem. I was thinking, if we go slow, then we may take another class. But if we finish the chapter, then let's do the exam on Tuesday.
We can still do it Thursday.
And do you want me to start next chapter on Tuesday?
Yeah. I can't come in on Thursday.
What?
I can't come in next Thursday because I have my client.
Well, that's a different situation which we can work on, but this is the overall class decision which we are looking at. If I'm still doing the exam on Thursday, I don't mind, but then I'm not going to waste the Tuesday class.
Can we review and then after done reviewing, can we start the next chapter?
Okay, we can do a little bit of review. I'm not again giving an entire class for review. It's already done, posted. Yeah, I did posted the homework today, which is due on, I think, no, what is the date? Today is Thursday. I put it for next Tuesday, I believe. Yeah, March 28th or something.
That's the Thursday.
28th, okay, no, 26th, I believe. I put it for 26th, isn't it? Or 28th, I'm not sure. Just check. I'll always change the due date if I put something wrong, okay? I will definitely change the due date if it is shorter than the time usually I give you guys. Because, yeah, that's it. This is just another slide which just kind of gives you combustion of fuels, what is the heat change, and one more slide of food representations. 1 calorie is 1000 calories. Okay, so what are we doing? Let's decide that and then go.
Tuesday.
April 2nd. Okay, that's what I thought. I have given, that's what I thought. I have given you a lot of extra time. Yeah.
Can we just come in Tuesday, go over real quick, and then start the test?
Okay.
No.
No, we won't have time. No, we won't have time to do the review and then do the test. I don't do that. I will just give you the test for a day, of class. So Tuesday, what we are going to do is, we will bring your questions, we will review, okay? Like the last time, I will tell you, actually I have time to tell you guys what questions you will have in your exam, but I will do that on Tuesday. First half an hour we will use for the review, okay? And then I'm going to start chapter 7, okay? So make sure you will start studying this weekend for your exam and bring any topic which you are absolutely not sure on Tuesday. Did everybody hear that? Okay. All right. Now, you cannot do the exam on Thursday. So.
I'm not sure. I get my car fixed at 9:30 in the morning in Rumford.
Okay.
And it's supposed to be done by 12.
Okay.
It'll take an hour to get here.
Okay.
So he might be done a little bit before, so it's either going to be late or it's going to be on time.
Okay. If it's up to you. If I don't want you to rush and speed or anything and get into an accident or get a ticket or something because and get here with the anxiety and do the exam. So if you want to do the exam on some other day, we can arrange for that. What do you prefer? You want to take a chance, or you want to do the exam on some other day?
Well, if I do end up being late, could I like go past the class time? Because I don't have another class on Thursday. Just had this week. Like, can I stay past 2? Is there another class in here? I shouldn't really be that late.
Okay. Let's see. There is a class right after here, but I guess we can move from here to upstairs, or worse in worst case, you can come to my office and finish the exam.
Okay. So I'll just